Welcome to G Fun Facts Online, where we dive deep into the most fascinating corners of our universe. Today, we're putting on our detective hats and stepping into the cosmic crime scene that is our own Milky Way galaxy. You see, our galaxy isn't just a serene collection of twinkling lights. It's a dynamic, sometimes violent place, and some stars are more than just pretty. They are cosmic culprits, erupting with intense bursts of radio waves and X-rays. And for astronomers, or stellar detectives as I like to call them, these emissions are vital clues, helping us understand the extreme physics at play. We're delving into what we can call stellar forensics, piecing together the life stories of some of the most unique and powerful stars out there. First, let's tune into the radio universe of stars. It might surprise you, but a whole variety of stars literally shout at radio frequencies. We're not talking about your average, quiet, sun-like star here. These are often objects undergoing dramatic events or possessing some seriously extreme characteristics. By listening to these stellar radio waves, we get unique insights into how stars are born, how they evolve, how they interact with their cosmic neighbors, and eventually, how they meet their dramatic ends. So who are these noisy stellar characters? Well, there are flare stars. These are often dim red dwarf stars that can suddenly, unpredictably, get super bright across the entire electromagnetic spectrum, including radio waves. Think of them like solar flares, but on other stars, driven by massive releases of magnetic energy. Our closest stellar neighbor, Proxima Centauri, is actually a flare star. Then we have interacting binaries. These are systems where two stars are locked in a close orbital dance. They can be strong radio sources, especially if one star is greedily pulling material from its companion, or if their powerful stellar winds collide. Imagine this: a white dwarf and a red dwarf star zipping around each other every 2 hours were recently found to be emitting radio pulses. That discovery, by the way, was noted in March 2025. Science marches on. Pulsars and magnetars are next on our list. These are the super-dense remnants of massive stars that went out with a bang, a supernova explosion. Pulsars are rapidly rotating neutron stars, sweeping beams of radio waves through space like cosmic lighthouses. Magnetars are a special, even more extreme kind of neutron star. They have magnetic fields trillions of times stronger than Earth's. It's almost unimaginable. These magnetic behemoths can produce bright, fleeting radio emissions, sometimes right after an X-ray outburst. In fact, the very first fast radio burst, or FRB, detected within our own Milky Way, was traced back to a magnetar. Even stars in their golden years, like red giants and supergiants, can get in on the radio action. They emit radio waves from layers in their atmospheres, called radio photospheres. Studying these helps us understand their complex, dynamic atmospheres, which are often characterized by pulsations, shocks, and significant mass loss. And let's not forget the babies of the stellar world, young stellar objects, or YSOs, also known as T-Tauri stars. These are young stars still in the messy process of formation. They're known for high levels of magnetic activity and can be surprisingly overluminous in radio waves, compared to what we'd expect from their X-ray emissions. This is a curious phenomenon tied to something called the Gödel-Benz relation. How do these stars generate radio waves? Several cool physical processes are at play. Gyrosynchrotron radiation happens when mildly relativistic electrons spiral in magnetic fields, common in solar flares and active stars. Then there's the electron-cyclotron maser instability, or ECMI. This is a coherent emission process that can produce incredibly bright, beamed radio waves, possibly responsible for some intense stellar radio bursts, kind of like Jupiter's own radio emissions. Plasma radiation, arising from oscillations in stellar plasma, helps us probe plasma density and the structure of stellar coronae. And finally, thermal free emission can come from ionized gas in stellar winds or X-ray heated coronae. Modern radio telescopes are our ears to the radio cosmos. Instruments like the Low Frequency Array, LOFAR, the Very Large Array, VLA, The Australian SKA Pathfinder, ASKAP, and Meerkat are totally revolutionizing stellar radio astronomy. They conduct sensitive, wide-field sky surveys, and they've been crucial in identifying new classes of radio transients and studying known sources in much greater detail. For instance, that peculiar system with a white dwarf and a red dwarf emitting radio pulses? That was pinpointed thanks to LOFAR observations. Another super exciting area is the search for radio signatures from star-planet interactions. This could offer a brand new way to detect exoplanets and even measure their magnetic fields. Now let's switch wavelengths and peek into the X-ray universe of stars. Stars also emit X-rays, and these high-energy photons reveal some of the most energetic processes happening in their atmospheres and surroundings. X-ray astronomy lets us study things like stellar coronae, the hot outer atmospheres of stars, as well as material accreting onto compact objects, and the violent aftermath of stellar death. Which stars are X-ray emitters? Young, active stars, much like our Sun but way more energetic, have hot coronae heated by magnetic activity that glow brightly in X-rays. Flare stars, which we know for their radio outbursts, also produce significant X-ray flares. Massive stars are another source. These cosmic giants possess powerful stellar winds. Shocks within these winds, or collisions between winds in binary systems, can heat gas to millions of degrees, causing it to emit X-rays. Then there are X-ray binaries. These systems usually consist of a normal star and a compact object, a white dwarf, neutron star, or even a black hole. Material gets pulled from the normal star onto the compact object, forming an accretion disk that becomes incredibly hot and shines brightly in X-rays. Some X-ray binaries, known as microquasars, also launch powerful radio jets. We'll come back to that synergy. Magnetars, those highly magnetized neutron stars we mentioned earlier, are prolific X-ray emitters. Their X-ray emission is thought to be powered by the decay of their immense magnetic fields and can be highly variable, often featuring bright X-ray bursts. And of course, supernova remnants, or SNRs. These are the expanding shells of gas and dust left behind after a star explodes. They are heated to millions of degrees by shock waves, producing bright X-ray emission. These X-rays allow astronomers to study the elements ejected by the explosion and the physics of the blast itself. What are the mechanisms behind stellar X-ray emission? Coronal heating is a big one. Magnetic fields in the outer atmospheres of stars can get tangled and release energy through magnetic reconnection, heating the plasma to X-ray emitting temperatures. This is seen in Sun-like stars and flare stars. Accretion shocks are key in X-ray binaries, where material falling onto a compact object releases gravitational potential energy, heating up to extreme temperatures. Wind shocks in massive stars occur when fast-moving stellar winds collide with slower wind material or with the winds of a companion star, creating shock waves that heat gas to X-ray temperatures. And in some extreme environments, like around pulsars or in the jets of microquasars, high-energy electrons can produce X-rays via processes called synchrotron radiation and inverse Compton scattering. Our X-ray eyes on the sky include telescopes like NASA's Chandra X-ray Observatory and ESS XMM-Newton. These have been instrumental. For instance, Chandra observations were key in identifying X-ray emissions from a newly discovered strange object in our Milky Way that also emits radio waves. And future missions like Athena are poised to make even more profound discoveries, exploring stellar winds and the hot, energetic universe in unprecedented detail. Now, here's where it gets really interesting. When stars shine bright in both radio and X-rays. Studying these emissions simultaneously gives us a much more complete picture of the physics involved. Some of the most intriguing stellar objects are luminous in both. Flare stars, for example, show correlated increases in brightness across radio and X-ray wavelengths during a flare. This suggests a common origin for the accelerated particles that produce both types of emission. X-ray binaries, especially microquasars, are fantastic examples. The accretion disk in these systems emits strongly in X-rays, while relativistic jets launched from near the compact object are powerful radio emitters. Understanding the interplay between this inflow of matter and the outflow in jets is a key area of research. Magnetars often exhibit radio pulses following X-ray outbursts. This provides crucial data on how their extreme magnetic fields dissipate energy. The magnetar SGR 1935 plus 2154, for instance, was observed to produce a powerful radio burst accompanied by X-ray bursts. And remember those young T-Tauri stars? The relationship, or sometimes the deviation from it, between their radio and X-ray luminosity, that Gödel-Benz relation we touched on, helps constrain models of their magnetic activity and flaring mechanisms. So what do we learn from these combined observations? We can trace particle acceleration by seeing how radio and X-ray emissions vary together during events like stellar flares. We can probe accretion physics in X-ray binaries by monitoring the X-ray inflow and the radio outflow. We can understand stellar magnetic activity, as these fields are central to many high-energy phenomena. And importantly, we can identify new types of objects. A very recent discovery, reported in May 2025, highlighted a strange new object in the Milky Way, about 15,000 light-years away. This object, SKA APJ18320911, emits X-rays around the same time it shoots out radio waves, with a repeating cycle of every 44 minutes during its active periods. It's the first of the long-period radio transients, or LPTs, to also be detected in X-rays, deepening the mystery of what these things are. The Milky Way just keeps surprising us with these exotic stellar objects that really push the boundaries of our understanding. These long-period radio transients, or LPTs, are a new class, exhibiting bright bursts of radio waves every few minutes to several hours. The X-ray detection from SKA APJ18320911 adds a new dimension to their study. Potential candidates for LPTs include highly magnetized dead stars like neutron stars or white dwarfs, or maybe something entirely new. Another LPT, Gleam XJO704-37, has even been found with an optical counterpart, meaning we can see it in visible light too. And the connection between magnetars and fast radio bursts is a hot topic. While most FRBs come from other galaxies, the confirmation in 2020 that an FRB originated from the galactic magnetar SGR 1935 plus 2154 was a landmark discovery. It provided strong evidence that at least some FRBs are produced by magnetars. Studying magnetars like SGRO 501 plus 4516, which is a rare, fast-moving magnetar whose origin is a bit uncertain, it might not be from a typical supernova, could further illuminate how these objects form and their connection to FRBs. Plus, the discovery that a white dwarf and red dwarf star orbiting each other can emit radio pulses has expanded the types of stars known to produce such signals. It used to be thought that this was mainly the domain of neutron stars, but not anymore. So this is stellar forensics in action. By studying these radio and X-ray emissions, we uncover so much. We understand stellar evolution, from the active nurseries of T-Tauri stars to the explosive deaths in supernovae and the exotic remnants like neutron stars and black holes. We probe extreme physics, because these emissions originate in environments with intense magnetic fields, incredibly hot plasmas, and matter accreting onto compact objects. They're natural laboratories for testing fundamental physics. We investigate stellar magnetism, as magnetic fields are the engine behind many of these phenomena. And, super excitingly, we can characterize exoplanet environments. Radio emissions resulting from the interaction between a star's wind and an exoplanet's magnetosphere, called star-planet interactions or SPI, could become a novel way to detect exoplanets and even characterize their magnetic fields, which is a key factor for habitability. While conclusive detections are still emerging, systems like Proxima Centauri are prime targets for this research. The future is incredibly bright, both in radio and X-rays. The quest to understand the most energetic and unique stars in our galaxy is far from over. Upcoming and future telescopes promise even greater sensitivity and new observational capabilities. The Square Kilometer Array, or SKA, will be a game-changer for radio astronomy. It will offer unprecedented sensitivity to explore faint radio signals from distant stars and potentially uncover entirely new classes of radio-emitting objects and phenomena, including more FRBs and those elusive signatures of star-planet interactions. On the X-ray front, advanced observatories like ESA's Athena X-ray Observatory will provide high-resolution spectroscopy and deep imaging. This will enable detailed studies of hot gas and supernova remnants, the atmospheres of massive stars, and the accretion processes around black holes and neutron stars. By combining radio and X-ray observations with data from other parts of the electromagnetic spectrum, and even other cosmic messengers like gravitational waves and neutrinos, an approach called multi-messenger astronomy, stellar forensics will continue to unveil the secrets of our galaxy's most captivating inhabitants. Each new detection of a peculiar radio flash or an X-ray burst adds another piece to the puzzle, painting a more complete and absolutely fascinating picture of the dynamic universe we live in. That's all for this episode of G Fun Facts Online. Join us next time as we continue to explore the wonders of science. Thanks for listening.